So we've just completed another cycle of the Sea Ice Outlook that was reported on with the Sea Ice collaboration team. I think Uma gave a presentation, a nice presentation of that in August. So there's been interest in how to systematically evaluate the Sea Ice Outlook models, the models that participate, how to evaluate their performance with an eye to improving predictions, or perhaps at least just to characterize how the predictions are doing. So today we'll hear two presentations on Sea Ice Outlook model evaluation and avenues for improvement. And we have two well-respected speakers on this topic for our meeting, and I'm very happy to have them both here presenting for us. So our first speaker is Ed Blanchard-Wrigglesworth. He is a research assistant professor in atmospheric sciences at the University of Washington in Seattle, and he will be presenting on forecast skill of the Sea Ice Outlook, challenges and opportunities. Ed?
Great. Well, thanks, Richard and Hazel, for those kind words and introduction. And I hope you can see this, my introductory slide.
That's good.
Okay,
yeah.
Great. So I want to give a fairly quick kind of bird's eye picture of the Sea Ice Outlook and sort of where we're at and the skill that we're finding and some issues that we're finding or some characteristics of the Sea Ice Outlook forecast as a whole, and some of the both kind of challenges and opportunities that I think this presents us. And I want to, some of the results you'll see are sort of part of the manuscript that's in preparation. And you can see, I want to acknowledge my co-authors. And I also want to acknowledge the wider SIPIN2 team listed there in blue. And also very importantly, and there's too many to list here, but to all the contributors that have submitted and contributed forecasts throughout the years. Okay, so how is, first I like showing this figure, which is courtesy of Larry Hamilton, and this shows the number of contributions of forecasts that we get every summer since we started the Sea Ice Outlook in 2008. And they are color-coded by the methodology that the different groups use. And the sort of, first kind of take-home message is that this graph's been getting bigger, right, with time. So that's a great sign that as a community effort, the Sea Ice Outlook has been growing over these last few years, well, from the beginning. And we're sort of perhaps plateauing over the last few years to just over about 100 forecasts per summer, which is about 30 each month, since we've traditionally had 3 sort of submission periods in early June, early July, and early August. And by looking at the colors, you can see that especially over the last half of the period, it's been mostly dynamical modeling submissions or statistical model submissions. So sort of quantitative methodologies, which are from the bulk of the Sea Ice Outlook. So I will point out that when you do plot 2022, it's actually the first year we've had a bit of a drop in those numbers, but we hope that's sort of a kind of temporary blip. And I think overall, getting feedback from the community, like, it's heartening to see that it's been a sort of well-followed exercise, and overall, I think this is a positive story. Okay, so when we look at the actual forecast, here I show the observed time series of September sea ice extent in observations in black, and the forecast, the Sea Ice Outlook forecasts, is sort of that kind of browny orangey color, and where the sort of the middle circles are the median of the July Sea Ice Outlook forecasts, and then the spread, the sort of envelope, is the interquartile range. And this has kind of been one of our sort of standard figures that we produce every year, and so this is updated through to this year. And if you look at this, and your kind of first impression is that we're perhaps not doing super well, then that impression is, I think, quite valid. And so to quantify the skill, one of the things we've done is we've calculated the root mean square error between the forecasts and the target, the observations, and that is shown on the left panel. And I show quite a few kind of metrics here, so let me walk you through them. The different colors are the forecast to the sea ice outlook. In red, that is calculating the root mean square error of all the individual dynamical models. And as we go from left to right, I show the different initializations. So June, the forecast that gets submitted in early June, July is early July, August is early August. And that's been a traditional kind of sea ice outlook period. So since 2008, we've always had those three sort of forecasting initializations. And since 2021, we've also added early September. And the reason why it's dashed is because we just have 2 years for September. So, you know, it's a much smaller kind of sample size. But okay, so the different colors are the dynamical in red, the statistical in magenta, and then the blue is the scale of just the median of all the sea ice outlook forecasts. So that previous figure I showed, that would be equivalent to the July root mean square error. And when we think about forecast skill metrics, it's very important to have a benchmark forecast, you know, something that you compare to. And we normally use either climatology or maybe a linear trend forecast and a sort of damped persistence or persistence benchmark. And so these are the two benchmarks I use. The continuous black line, which is flat, that is the skill if you just use a linear forecast of past Septembers to forecast the following summer. And you extrapolate that linear time series. And then the dashed black line, the thin black line, that is using a damped anomaly forecast using the first of each month, and the known sort of persistence of sea ice anomalies, right? So we know that sea ice extent has a seasonal persistence timescale. So if you have a negative anomaly in July or August, you're quite likely to have a negative anomaly in September. So if you make a very simple statistical forecast using that methodology, you get that dashed black line. And there's quite a bit to read from this figure. One is that overall, when you make the sea ice outlook median forecast is higher skilled than the kind of full suite of the either statistical or dynamical models. The dynamical models perform a little worse than the statistical ones. We do see an improvement from June through July, August, September. You know, as the lead time decreases, we see an improvement, but it's relatively modest or fairly flat. And then the other main result, I think, is that it's really hard to beat that damped anomaly benchmark, which is what you really want to be doing if we're going to all the trouble of, you know, creating these forecasts, which, you know, take a lot of resources. And so, you know, we want to be below that, eventually below that black dash line. And then, yes?
Mike Steele is asking how the blue line is below the other two curves.
Well, it's because it's a better forecast. And what's happening here is that you're probably canceling models, like individual submissions that are either really too low or too high. So for example, if the temperature tomorrow is 70 degrees Fahrenheit, and I have two forecasts, one is 60 degrees Fahrenheit, the other one's 80 degrees Fahrenheit, the individual forecasts are off by 10 degrees, but if I take the median of the two, it's a perfect forecast, right? So
I see.
That's probably what's going on in the background. And then on the right, I show the forecast error. It's a scatter plot between what we observed to be the deviation from the expected linear value of that year, which can be, you can think of this as a metric of like, you know, how extreme was that year, like positive or negative, compared to maybe where that linear trend expects you to be. And then the forecast error on the y-axis, right? And you can see there's a linear slope, which basically means that years that are more anomalous, our forecast errors tend to be larger. Okay, so something else we've noticed is that there is a sort of a 1 year persistence between the observations and then the forecast. And what I mean by that is that if in observations we have a very low year, for example, in 2012, we've noticed that the forecast the following year tend to also be low. And what I show on the left is the top left panel is a very similar figure to my first slide, which is the observed sea ice extent and then the sea ice outlook forecasts. And then the bottom panel, we're shifting that observed time series by 1 year, right? So for example, on the x-axis in 2013, that shows the forecast for 2013 and the observations for 2012. So there is this sort of very curious kind of a feature which we don't really fully understand, and we don't really expect it, because in observations, there isn't really a 1 year sort of memory in September sea ice extent. So this is something that, you know, we kind of noticed years ago, and it's still, as we update these time series, it's still kind of a feature. And this is kind of a curious result that we don't fully understand. Okay, so I did mention that in 2021, we added forecasts in September, in early September. And historically, I think we didn't do this because, you know, there was a kind of feelings that, well, by early September, you're already in September, you kind of know what the answer is going to be. So is there much to learn from this exercise? And you know, one of the features that I didn't really mention is that throughout the years, we've seen that you know, pretty much during every sea ice outlook forecast, there is a really big spread in the models, right? Some models always have or tend to have low forecasts, say in the 3.5 or 4 million square kilometers, and other forecasts have 5, 5.5, even 6. So we've noticed that there's always like a big spread. And so one of the questions we had is that, well, if you know, would that spread kind of collapse if you made a forecast in September, and how much better would the skill be, right? And so what I show here, these are the results in 2021, which is the first year we did this. So these are all the forecasts from either the dynamical, statistical, or machine learning models during 2021, during the June, July, August, September forecast periods. The lines are the means of each cluster, right, of each technique. And you can see that, and then the gray line, the gray flat line at around 4.9, that's the observed value, right? So that's the target. And you can see that throughout the forecast period, yes, the forecast is slowly improving, or they're getting to that 4.9 forecast, but the spread, it almost remains the same, right? You know, by early September, you might think, well, you know, the forecast should be converging, but we don't really see that. And one kind of very simple exercise we did last year to kind of try and understand or put this into a bit more better perspective, we thought, okay, well, we know by early September, we know what the August 31st September sea ice extent, right? So, you know, if you place yourself on September 1st, you know how much sea ice extent you have on August 31st. And we thought, okay, well, if we use all the past historical changes of daily sea ice extent throughout September, what forecast would you make, knowing how much sea ice you have on August 31st and knowing sort of historical tendencies or changes of daily sea ice extent? And we did this last year. And if you do that, you basically get an expected mean September sea ice extent of between 4.8 and about 5.4, right? And that's what I show here. So this kind of plume, that's the observed August 31st sea ice extent in 2021, plus each year here is 1 year from 87 onwards, which is when we have daily data, like a time series of that extent, right? And then you take that mean, and that's where the arrow takes you to. So each of these black dots would have been one forecast for 1 year, right? And you can make a forecast or a range using those expected values. And then on the rightmost column in colors, these are the forecasts in September 2021 from the sea ice outlook. So if these forecasts are below the kind of black cluster here, that means that forecast would have required an unprecedented rate of change in September sea ice extent. And so we can use this, I think, to sort of place either confidence or to kind of, I think, highlight issues in some of our forecasts. What I think is really interesting is that this year, so this is the second year in 2022 that we've done this September sort of forecast. On August 31st, we almost had exactly the same sea ice extent as last year. So when you do the same forecast with the same methodology, you almost get the same range of that. On September 1st, we would have known, okay, we're going to be somewhere between 4.8 and 5.4. And the range of forecasts this year in the CIS outlook was much kind of narrower and closer to that observations, right? And that's shown in the rightmost column here, the September 22 CIS outlook. So is that improvement? Is that by chance, or is it a sign that, you know, kind of the different modeling centers are sort of taking this information and sort of going back to the model development, or how they bias correct the forecast and sort of, you know, improving their forecasts? That's a question mark, but I think it's nice to see that development. And then the last thing I want to talk about is something else we've tried to do some research on, is the forecast initial conditions. We know that a forecast skill depends, or one of the things it depends on is the initial conditions. So we invited the contributors to share those fields with us, and about 5 or 6 modeling centers have done. So what I show you here, the top row is the sea ice concentration in the initial fields at initialization. And then the bottom row is the sea ice thickness fields at initialization. And you can see the different dates there. Like kind of the big picture here is that normally, or what we're finding is that the sea ice concentration across the different initializations agrees relatively well across the different models, but the sea ice thickness in the bottom row is quite different between some forecasts and others. So when you take the sea ice volume, when you integrate these qualities, what we find is that there is a big spread, right? And so what I show here is both in 2020 and 2021. Each dot here is how much sea ice volume these forecasts had at initialization, and the x-axis is the day of initialization, right? And so for each panel, you kind of see 3 clusters along the x-axis, and those are the June, July, August initializations. The thin black lines are June 1st, July 1st, August 1st. So you can see, you know, those kind of clusters, but you can see quite a lot of spread along the y-axis, sorry, right? And that just means that even on the same, or about the same day of initialization, models have quite different initial conditions. And then, you know, the kind of next obvious question is to ask, well, does that affect what they're forecasting? So here is the scatter plot of the x-axis is how much sea ice volume they have at initialization, and then the y-axis was the sea ice outlook forecast. And I've just added 4 months, like 2 months from each year, to get a bigger sample size. But you can definitely see there's a little bit of a positive correlation there, right? Which it might be what you expect, that if you have more sea ice volume at initialization, you end up with a larger sea ice extent forecast in September. Okay, so a bit of a summary. I think overall it's undeniable that we've, you know, the sea ice outlook has been successful in creating this network and this kind of like international group of sea ice forecasters and modelers, and we've learned a lot about where we're at, about these the skill of the current systems. We're finding that I'd say the skill is relatively low, or definitely a bit low from what we expect of either simple benchmarks, but also I didn't have time to talk about this, from historical hindcasts or perfect model systems. And so the, you know, sort of where we're now is, well, what's the optimal way to improve the skill of these forecasts, right? We have finite resources, and there's many ways that, or many things you could work on. You can work on initial conditions, or is it model physics that are more important? Both perhaps, but and then to kind of hopefully introduce Mitch's talk, we know that there's kind of a need for standardized model skill comparison. And so without stealing any more of Mitch's thunder, I'll let him carry on.
Thanks very much, Ed. Just to clarify a few things about participation, would you agree that more models, or there are more submissions in general for the June and July deadlines than there are for September, and perhaps for August as well?
Well, definitely more than September. So for June and July, we normally, over the last few years, we've probably had in the ballpark of in the mid to high 30s. And for September, I think we've been in the low 20s. But that's somewhat to be expected, because, you know, it's been a new effort, and it adds on. You know, we know that we're very cognizant of the kind of contributors' time, and that this is sort of a kind of a voluntary exercise in some regards. So I can't remember the exact wording in the call, but I think, you know, September's been as a sort of new invitation for people, perhaps it's just a little bit harder for people to go from 3 submissions to 4. And I do think August maybe have a few less than in June and July, but it's still a pretty high number of forecasts.
And in anticipation of Mitch's talk, let me ask if, well, the North American Multi-Model Ensemble, the seasonal Ben Kirtman seasonal prediction systems, I think they got their start around 2011 or so. So I think your slides do show that there's an increase in modeling participation in the years after that. Is that generally the case?
Yeah, although it's a fairly gradual increase. I'm just looking back at that slide, and I can share my screen again if it's useful.
Oh, maybe not.
But it's a good question, and I hadn't really thought about it. But I don't really see like a step change in 2011. It's more, it's maybe
it's
more
delayed. Yes.
Yeah. But I think perhaps it was arguably, although maybe you'd expect that in 2012 to 2013. I was thinking, did the record low in 2012, and that increased interest in Arctic sea ice forecasting and variability, did that kickstart? And in fact, actually 2013 is the only other year apart from 2022 where you see a bit of a drop from the previous year. But sometimes, because of getting the resources to make these forecasts, grant writing and all that, right? If people were motivated in the fall of 2012 or throughout 2013 to make forecasts, maybe it took a year or two, right, for that growth to show up.
Right. I think our first forecast was submitted in 2013, I think.
Yeah, and it's interesting. 2013 actually is one of the years that a lot of these hindcast papers were published. I think there's like 3 or 4 kind of become fairly classic hindcast sea ice study papers, and they all came out in 2013 or 2014.
Is there another quick question for Ed from the group?
Just a quick one from me. I was looking at the same graph. In 21, you had more, you had something called other in terms of a category, and it dipped in 2022. And so what was the other? Just curious.
So that good eye. That was machine learning, which we classified, at least for that year's other. And I think we had some internal debate as to whether that classification, since they are a statistical model, or they arguably within that category. And I think for this year we ditched that kind of distinction. But yeah, most of those other in 2021 were the machine learning.
All right. Thank you, Ed. Well, let's go to the next speaker then. Our next speaker is Mitch Bushuk. He is a research scientist at the Geophysical Fluid Dynamics Laboratory in Princeton, and he will present on a multi-model comparison of retrospective September Arctic sea ice seasonal prediction skill. And that looks good. Mitch, we can't hear you.
Testing 1, 2, 3.
Yeah, that's good.
Okay,
yeah.
Great, wonderful. Just 1 second. Great. Yeah. So thanks, Ed. That was literally the perfect introduction to my talk. And yeah, so I'm going to be speaking about this emerging effort. Sorry, I'm having some screen issues here. Going to talk about this emerging effort to do a sort of apples to apples retrospective skill comparison of Arctic sea ice seasonal predictions. And as you can see from the massive co-author list, we've got about 50 people involved in this. So it's really a big community effort within the Sea Ice Outlook contributors community. And so I want to say a big thanks to all my co-authors listed here. Also a big thanks to the SIPN team for kind of making the Sea Ice Outlook happen for the last 15 years or so now. And also to NSF for supporting SIPN 1, 2, and hopefully 3. Okay, so as Ed introduced, and this is a slightly different figure than what Ed showed in his talk, but every summer we get these Sea Ice Outlook forecasts submitted, and then the observed value comes in at some level, but there's always some models that look good in a particular year, some models that look less good. And there's always this question when you see these graphs of, on an individual model level, is there prediction skill? And on a multi-model level, is there prediction skill? So regarding this question, there's this interesting, what I would call a tension in the sea ice prediction literature. So on one side, you have these studies that have been written focused on the sea ice outlook. And this is a version of the figure Ed showed earlier from Larry Hamilton's paper, which basically shows the point that Ed made, which is that the sea ice outlook models, if you look at the SIO median prediction, for example, don't look particularly skillful. And that's led these studies to make statements along the lines of evaluation of these forecasts has revealed that regardless of method, forecasts struggle when the observed sea ice extent minima depart strongly from the linear trend. And we find that median SIO predictions outperform naive predictions, although sometimes not by a wide margin. So what they're saying here is that there's a little bit of skill, but compared to just a very basic linear trend, or as Ed showed, damp persistence forecast, there's not much skill to be had in the SIO predictions. And there's a tension because, as Ed also alluded to, if you look at these hindcast or retrospective seasonal forecast studies, there's been a whole host of different papers published claiming that it is possible to develop a seasonal prediction system that can skillfully predict the detrended interannual anomalies of Arctic sea ice extent. And these studies use dynamical models, statistical methods, all sorts of different techniques. And nearly all of these papers has some sort of sentence in it along the lines of, for most predicted months and lead times, trend independent forecast skill exceeds that of an anomaly persistence forecast. So you've got all these studies saying that skill is possible, and we've produced methods to skillfully predict sea ice, but then the sea ice outlook real-time predictions have not really borne that out. So what's going on here? So in January 2021, we had a really invigorating and exciting meeting that brought the whole SIO community together in this contributors forum. And Mike Steele and others wrote this nice sort of meeting summary paper that was published in BAMS later that year. And in my mind, the most critical thing that came out of that meeting was a whole host of different kind of recommendations for the future of the sea ice outlook. And two of these recommendations that I want to highlight here were a need was identified to do sort of an apples to apples comparison of the skill of dynamical and statistical models using ideally a common time period and also the same skill metrics so that we can sort of put all the models on a common footing and just get a sense of where we are at as a community with regard to our prediction skill. And then a related secondary goal was this need to create a database of these retrospective predictions to allow for further analysis of these seasonal sea ice predictions. So in response to that, we later that year, this was in late 2021, we came up with this data request. And we emailed all the SIO contributors and we requested retrospective seasonal predictions of September monthly mean, Pan-Arctic sea ice extent, regional sea ice extent in these 4 regions, grid point level sea ice concentration predictions. And then where applicable, we asked for the initial conditions of sea ice concentration and thickness from the dynamical models, and also ensemble data if it was applicable. And so we requested predictions on the SIO initialization dates of June 1st through to September 1st. And a key point is that we requested a minimum reforecast period of at least 20 years, preferably from 2001 to 2020. And if groups could submit more years, that was encouraged. And then we also asked for some metadata describing the design of each forecast system. And so here's what we received. We got prediction data back from 17 different dynamical models, 17 statistical models, and 1 heuristic prediction. And this was really a global effort. Like we got contributions from 11 countries spanning Europe, Asia, and North America. And this totaled nearly 3,000 independent predictions of September Pan-Arctic sea ice extent. After receiving the data has now been all formatted into a common format, which hopefully will make future analysis for others easier. And this represents the most comprehensive data set of multi-model sea ice predictions that's been assembled to date. And we're really hoping that, beyond just this review paper, which we're currently working on, it's going to hopefully be a community resource that sort of scientists within our community can use and kind of dig in further with kind of more advanced questions in the future. This table shows some more details of what we actually received. So each model, so these are the 17 statistical models that submitted. And so each model submitted some time period, some set of initialization dates, and then every model submitted pan-Arctic sea ice extent. And you'll see that a good number of these ones also submitted regional extent, and then some submitted sea ice concentration maps as well. And then here's what we got from the dynamical models. Most of these submitted spatial fields of sea ice concentration, as well as regional and pan-Arctic extent, and most of them also submitted ensemble data. So we really got a nice contribution of data from 34 different systems in total here. And then we also got one heuristic prediction. This came from the NCAR sea ice pool, which is performed every summer in early June. Okay, so just as a first look at how we're doing, again, going back to that figure that Ed showed and was shown in Larry's earlier paper, you can make, so on the right here, I've made sort of a version of this figure using the retrospective prediction data set. And so the obs are shown in black, the red line shows the multi-model median, and then the gray band shows the interquartile range. And just using the I norm, you can see already that the multi-model median in this retrospective data set looks pretty good. It's clearly skillful. And if you just focus on the 2008 to 2021 period, you can compare to this plot and see that the predictions are doing quite a bit better over the sea ice outlook period. So this tension I alluded to earlier is still present here in the sense that the retrospective predictions are doing better than the SIO predictions did. Okay, so to get a bit more quantitative, we can look at prediction skill metrics. And I'm going to compare skill to two reference or benchmark forecasts, a linear trend climatology, and then the same damped anomaly persistence forecast that Ed mentioned. And just to show you the formula, the damped anomaly persistence forecast is constructed by taking the linear trend climatology prediction, and then adding to that the observed anomaly of sea ice extent at the initialization time. And then that anomaly is scaled by the observed autocorrelation between the initialization time and September sea ice extent, and then also scaled by the ratio of the standard deviation between the target time and the initialization time. And then I'm going to quantify skill throughout this presentation using the RMSE as Ed showed, as well as the anomaly correlation coefficient, or ACC, which is just the correlation between predicted and observed anomalies. And then I'm also going to show some detrended metrics, which instead of looking at the full anomalies, these anomalies are computed relative to a linear trend climatology. So the idea here is that we know that we've had a strong trend over the satellite era. And so the detrended metrics remove the trend signal and then ask if you can predict the interannual fluctuations relative to that trend line. Okay, so in terms of the trend climatology, you can see that for the full non-detrended ACC, even a linear trend is pretty well in ACC value of above 0.7. So it's capturing about half the variance of the interannual anomaly signal, just due to the fact that we have, of course, had a very strong trend over the satellite era. And then if you compare that to the damp persistence, which is shown in this solid gray line, you can see that by incorporating information about this year's anomaly, you get a clear boost in prediction skill, especially from September 1st and August 1st. And then as you go back to longer lead times, that damp persistence skill kind of converges to the trend climatology. Okay, so now we can add on to these plots some multi-model predictions. And so these are multi-model predictions computed using the dynamical models that were submitted. And the dashed black line shows the multi-model median prediction. The solid black line shows a multi-model mean, where the multi-model mean is a weighted mean, where the models have been weighted by their mean squared error skill score. And what we see for both these multi-model predictions is that compared to the damped anomaly persistence, if we focus on the detrended ACC here, you can see that the models are doing a much better job than this reference forecast at capturing these interannual fluctuations in sea ice extent. And even going back to June 1st, these multi-model forecasts have ACC values of above 0.7. So quite a bit of skill for these detrended interannual anomalies. And okay, and now I'm going to show you a pretty busy plot, but I think a really exciting plot. And so we can add to this now all 17 dynamical models that submitted forecasts. And so there's a lot going on here, of course. But the key point I want to make is that there's sort of this plume of models that show skill ranging from, let's say, 0.4 to 0.6 correlation from June 1st, going up to correlations in the 0.8, 0.9 range from August 1st and September 1st. And so what we're seeing is that sort of nearly all the models are showing some skill at predicting detrended interannual anomalies of Pan-Arctic sea ice extent. If we look at, oh, sorry, was there a question there? Maybe not. So if we look at September 1st, you can see that the best models are essentially tied with this solid gray line. And so that's saying that damp persistence is a very good benchmark, as Ed already stated, if you initialize on September 1st. So the best models are tied with damp persistence. Most models are losing to damp persistence because they're making some errors in their initialization. If you go back to August 1st, you start seeing that there's a group of models that are starting to beat damp persistence. And then by July 1st and June 1st, nearly all the models are beating damp persistence. One other point I'd like to make here is that this gold line really stands out. And so this gold line is the ECMWF CS5 model. And ECMWF really does stand out, especially from July 1st and June 1st relative to the other models. And it has skill that is pretty well separated from any other dynamical prediction system. And so this seems to be sort of an outlier on the positive side. Okay, so here's the same plot now for the 17 statistical forecast systems that submitted. So starting again with the multi-model forecast, you can see the black solid line, the weighted multi-model mean looks quite skillful. The median prediction also has quite high skill going back to June 1st. Again, we see this, what I would argue is kind of a plume of models that all has sort of similar skill within this band. One difference here is that we do see some models that don't have much skill within this, this group of models. And then again, we have a couple outlier models. So there's two models that perform very well and have much better skill than any other system that was submitted. These systems are the red line is a multilinear regression model from the Alfred Wegener Institute. And the orange line is a machine learning based model from Kopri in Korea. And we've been digging into why exactly these models are doing so well and still trying to kind of figure that out exactly, how they're getting such high skill. And just to do kind of the head-to-head comparison here between dynamical and statistical models, this is showing detrended ACC kind of head-to-head for the models. And I think, you know, if you blur your eyes and take these as a whole, you would argue that the two forecast methods are performing fairly similarly, with maybe the exception that some of these statistical models are not doing as well. But overall, it seems that there's no clear advantage between dynamical or statistical. And then in each case, there's a couple outlier models that are doing very well. Great. So I think my time is going by quickly here. So so another question we've been really interested in is this question of whether or not sea ice predictability has been changing over time or not. And so this plot gets at that question. And what we're looking at here are mean absolute errors computed for each individual model, and then taking a multi-model mean of those mean absolute errors, and then plotting those as a function of time. And then the different colors show the forecast initialized at different lead times, going from September 1 back to June 1. And what you see is that there's kind of a baseline error level, maybe around 0.4 or so. And this time series is punctuated by these 3 years, 96, which we know was a big positive anomaly year, and then 2007 and 2012, which of course were big negative anomaly years. One point I'd like to make here is that, one thing to note is that the models generally are struggling with these extreme years. So the errors are largest in the extreme sea ice years. But if you look at this gray line, which shows the error made by a trend climatology prediction, there's actually an interesting kind of point to make here, which is that if you look at the improvements of the models relative to that trend climatology. So in this plot, positive values would indicate sort of added value on top of a trend climatology. What you see actually is that it's precisely those extreme years of 2007 and 2012 that stand out as having the largest improvements above and beyond the trend climatology. So I don't think it's quite fair to say that the models failed in these extreme years. I think actually a better way to look at this is that these extreme years had a combination of predictable variability and unpredictable variability. And the models were actually able to capture a sizable fraction of that predictable variability. But then there was, of course, some unpredictable variance that was not captured by the models. But in terms of the years that you'd want a seasonal prediction system, it would actually be 2007 and 2012, where they would have the most value. Great, so I think my time is basically up. So I'm just gonna zip through these last couple slides pretty quickly. But these are showing the similar sort of multi-model skill plots for regional sea ice extent now. And so these are showing the Alaskan region and just focusing on the detrended skill metrics. What we see here is that both the dynamical and statistical models do have skill at predicting Alaskan sea ice extent. Generally, it seems like the dynamical models are doing a little bit better in this region compared to the statistical models. And we find that that's also the case in the Siberian sector. So this region encompasses the Laptev and East Siberian seas. And again, we see that there's this group of dynamical models that seems to be doing quite a bit better than the statistical systems in this region. This plot shows the Canadian archipelago and Baffin Bay. Generally, skill is lower in this region, and this is kind of notorious as being a hard to model and hard to predict region. There are some models that do have some tantalizingly high skill, such as RASM and Biomass, for example, but also quite a few models that have fairly poor performance. And then the final region is this Atlantic region. And the models generally struggle to predict sea ice in the Atlantic region. It's important to note that the signal is pretty small here. There's not a lot of sea ice in these seas during September. And the sea ice that is there is quite difficult for the models to get, it looks like. Okay, great. So just to summarize the findings so far, Sea Ice Outlook contributors have created a new multi-model reforecast data set consisting of 17 statistical models, 17 dynamical models, and 1 heuristic prediction. We found that most of these models have pan-Arctic sea ice extent skill at the SIO lead times. And these results suggest that detrended ACC values of roughly 0.5, 0.7, 0.8, and 0.9 respectively could be expected at these lead times. We also found that most of these models have skill for regional sea ice extent, but the regional skill is generally lower than pan-Arctic skill and tends to have more spread across the models. And the Alaskan and Siberian seas are generally easier to predict and more skillfully predicted than the Canadian archipelago and the Atlantic regions. We found that the skill of the dynamical and statistical models is generally comparable for pan-Arctic sea ice extent, whereas the dynamical models appear to have a bit of an edge when you get down to the regional sea ice extent scale. And regarding sort of non-stationarity, there's no clear trends in prediction errors over time. The models generally struggle to predict the extreme sea ice years. However, they do skillfully capture some portion of these anomalies. So this is very much work in progress. So I'm really keen to hear if you have any suggestions or comments, would love to hear them. This analysis is very much still ongoing, and yeah, happy to take any questions.
That's awesome. Thanks very much, Mitch. So just a quick clarifying point here. So a system will submit, forecasts year after year, year after year. So these hindcasts are produced from what is likely the most recent version of these systems. So that might explain some of the difference in the skill between what has been submitted to the Sea Ice Outlook and the skill that you might see from this study. Although probably that's the difference is probably there are also some subjective questions associated with that.
Yeah, I fully agree. So the systems are constantly evolving, and likely the submissions were made with sort of the latest, greatest, best version of each center system. And so that could create higher skill in this data set compared to the SIO data set. But there's also a laundry list of other potential reasons for this discrepancy, which I'm happy to get into a bit more if others want to kind of talk about that more.
Okay, I saw a question first from Mike Steele. Would you like to unmute and ask your question, Mike?
Sure. Mitch, I know that, I guess there's been some talk, but can you summarize your conclusion with regard to the question you started with? That what is your feeling on this tension between SIO and retrospective forecasting?
Yeah, that is of course the elephant in the room. And I'm just gonna share my screen again here. So I've actually got a slide. I've got a slide kind of with the laundry list. So I don't have a super clear answer at this time. I suspect it's some combination of the factors listed on this slide. So I'll start with the point Richard just made, the fact that prediction systems are non-stationary and groups are likely submitting the best version of their prediction system. But there's also a number of other factors. Selection bias is an important one to think about. This reforecast exercise was an optional opt-in exercise. And so only groups that had skill presumably would want to submit reforecast to this exercise. So I think we're probably sampling the better models and probably excluding some of the poor models that are submitting to the SIO. So I think that's a factor. There could be differences between doing predictions in real time versus retrospective in terms of certain data not being available for near real-time predictions, or certain data sets maybe not being as rigorously quality controlled in real time. So it may be that real-time prediction is just inherently more difficult than doing these retrospective forecasts. I think, and Ed alluded to this as well, that I think bias correction is a really big thing to consider. Most of the retrospective models did perform a bias correction using their hindcast, which is going to improve your skill. But a lot of the CIS Outlook models do not bias correct, and that's going to tend to degrade the RMSE. It's important to note that for anomaly correlations that won't actually change the anomaly correlation, but the SIO record is so short that it's actually hard to rigorously compute a correlation over 10 years or so. The bias correction is definitely a factor. The one that I'm most afraid of is this 0.4, using future data. We got to make sure that none of the retrospective forecasts are allowing future data to corrupt the results at all. And future data may be sort of leaking in sort of nefarious ways potentially in some of these retrospective forecasts that are being submitted, which would of course bias the skill estimates high. And then the final point is that the inherent predictability may have changed. I think the results I showed today suggest that's probably not the case. But yeah, that's kind of the laundry list right now, but there's no super clear answer at the moment.
Okay, Jia Wang, could you unmute and ask your question?
Okay, so the retrospective model, I think it's we already done something like this, but we haven't started to do the seasonal forecast yet. Start from June, July, or August. We developed the model, the statistical model, using only the 6 teleconnection pattern indices. And the monthly indices we pick up from June, from January to August, in order to do the prediction for September. So our index range in these 8 months. So I think I'm writing a manuscript right now for something, and maybe sometime I present this to this group. And I think in near future, when we have a little manpower or after the paper out, and we will provide the projection. Our purpose is we don't use temperature. We don't use sea level pressure. We only use indices of 6 connection pattern before September. So I think that is I think very fit to this group, this topic. Thank you.
Well, I would encourage if your system has any skill to submit in real time to the CIS Outlook.
Our handcast correlation between the observation and then the model results are 0.78, quite high, but not quite high. It's 0.78. So I think low is a balance C. Of course, balance C have a very low variability, and it's not very good for statistical model because we need a random, we need a random time series and independent time series. So, but for other subregion, I think the correlations are about 0.76 to 0.78. So I think all over the 95 significant level. So.
Okay, Wisla, could you ask your question regarding the CMWF model?
Sure, thanks, Richard. My question is that the Pan-Arctic scale, the ECMWF was positive outlier, but when you show the regional analysis, this is to Mitch, that was not the case. Do you have any comments on that? Thank you.
Yeah, I noticed that as well. That's a great point. I don't have a great answer for that, I would say. One thing I can say is that I do know that ECMWF does have a pretty notable positive sea ice extent bias, especially in the forecast initialized from June. And so my suspicion is that that bias may be more easily linearly removable. In other words, bias correctable for Pan-Arctic sea ice extent. But then when you get down to the regional scales, the bias is harder to remove in a clean sort of linear way, and they aren't able to get skill. So my suspicion is that their model bias may be kind of coming in there and degrading the more local predictions, but that's just a hypothesis.
So just a quick follow-up on that. It might be possible that, or it is possible that there's a cancellation on errors on the regional basis, and when you look at just the scalar value, you get a perfect score, but it's not necessarily the same case if you do like IIEE analysis, integrated ice edge error analysis. So my point is that you might want to have a try at this and have a look at that particular model for just a 1 month or one September forecast and see whether that's the case.
Yeah, so I've actually checked that, and I didn't show it today, but for IIEE, ECMWF is actually one of the maybe the poorer third of models from June from June 1st, and then they do very well on September 1st and August 1st, and because they have very good initial conditions and a good atmospheric prediction. But I think their model bias is hurting the ice edge error at those earlier lead times. So yeah, I think you're bang on there. Yeah,
appreciate it. Thanks.
Young Chu, you have a question regarding initial conditions?
Right. Either Mitch or the Ed can answer that. Any comments on how important the initial conditions are in dynamic models from your analysis?
Maybe I'll let Ed answer that so I don't hog all the airtime.
Yeah, so we have what you might call kind of preliminary, or at least initial stages analysis, because we don't have that many contributions, right? So I showed those figures from the 2020 and 2021 sea ice outlooks, and we had about 4 or 5 models that submitted the initial conditions, and at least it's a fairly small sample size, but even within that group of 4 or 5 models, we were able to diagnose that they do have quite different sea ice thickness initial conditions, even on the same date or around the same date, and it does seem to have an impact on the sea ice outlook forecasts. And we would love to have a bigger data set, but hopefully that's something in the future that we'll be able to dig in better. And I know that I've talked to Mitch about this for the hindcast. If we could get those fields in the future, I think we'd be able to answer this question a lot better. But yeah, I mean, my hunch is that they do have an impact. I mean, they must. And I think it also, I didn't mention this, but I showed that the sea ice concentration looks better or more consistent across the different models, and the sea ice thickness is more inconsistent. But this makes a lot of sense with observations, because we have more accurate observations of sea ice concentration that the models then use to simulate. And sea ice thickness in the summer, gridded fields of observed sea ice thickness don't really exist, and models don't tend to simulate anyway that information. So I think it makes sense that there's a lot more uncertainty in the thickness than in the concentration.
Just quickly, Mitch, I think the call asked for initial conditions as well. So that's potentially an area for future work. Is that right?
Absolutely. Yeah. So a number of groups did submit initial conditions of thickness and concentration, and we're hoping we can do some of the analysis that Ed showed, basically with sort of more models, longer time series, just to sort of increase the robustness of what Ed showed earlier. That probably won't go into this review paper, I don't think, but we're hoping that somebody will pick that up in the future. And just actually one more comment to Yunju's question. We found in the GFDL model that you can explain essentially all of our skill for both regional and pan-Arctic sea ice extent just by constructing a multilinear regression model using the initial thickness and initial concentration that we use for the forecasts. So we think essentially all of our skill anyways is coming from initializing those fields and then just the model being able to sort of persist those anomalies forward in time. So I think I fully agree with Ed that they're critical.
Thanks.
It's the top of the hour for those who have appointments. Ed, could you unmute for your question?
Yeah, it's sort of a comment that for Mitch, that I don't think this sort of quite odd feature in the sea ice outlook that next year's forecasts are heavily influenced by the current year's observations. I don't think you saw that, right, in the hindcast?
Yeah, I've checked that in the hindcast, and as you would expect, given that it's not in the observations, it's also not present in the hindcasts. So the hindcasts don't have this curious kind of lag one year correlation, which I think is a good thing. I don't think you'd want them to have it, but then it's still, yeah, that question's still hanging as to why the SIO models do have it, of course. Yeah.
And Yvette, are you still here?
Yes, I'm here.
Very good.
So I have a question about the atmospheric forcing, because it's always a problem to have the right atmospheric forcing, and then the ice will depend upon that. So how can you dissociate your model scale in terms of ice prediction and circulation from the error that would be in the atmospheric forcing? And I gather that if you do a retrospective analysis, then you can use the same forcing, but when you do the forecast, all the model will use different atmospheric forecasts to force their model. So how do you dissociate the scale of your ice model, circulation model versus atmospheric?
You want to say a few words about your nudging work, maybe, Ed?
Yeah, so we think of the atmospheric part as that's what's, to a large extent, the unpredictable part, right, of the seasonal forecasts. But there's but that is still the case in imperfect model forecasts, right? None of these forecasts play the game of like, let's assume we know the atmosphere perfectly for the summer. Because we know that you're never going to be able to, that it's unpredictable, right? I think this is more, we know that the predictable signal resides in the sea ice conditions and probably the upper ocean, right? And we know that signal is enough to get a skill forecast from early June and early July. The issue, though, whether if a model did get the right atmosphere, did also get the right sea ice, I think it's valid, but we haven't explored that. I think, however, a related question, which has been bouncing around the community for years, was that the years where the atmosphere was more anomalous, that the forecasts were less skilled, but no one's actually shown that. So I think that's an open research question. And Mitch, I know you mentioned about my nudge work, but I was wondering, are these the experiments with Mitch or the ones where we nudge the atmosphere year round, or like with Letty? So
yeah, I guess I was going to make 2 points, I guess.
Yeah, go ahead.
Yeah. So I think a key point is the different systems all use different reanalyses to produce their initial conditions of sea ice thickness. And a lot of these systems are, forcing or nudging the atmosphere towards reanalysis, forcing an ice ocean model, for example, and using the winds and air temperature constraints to produce the initial conditions for ice thickness. And I think actually that's actually a big reason why ECMWF is doing quite well, is that they have a very good reanalysis forcing in addition to concentration and SST assimilation. And I think that's giving them a good constraint on initial thickness in June and July, even though they aren't directly assimilating thickness observations in the summer. So I think the reanalysis forcing is really critical for initialization. And then the point I was going to make regarding Ed's nudging work is Ed and Letty have shown that, and this is kind of just supporting your point basically, that if you take observed winds and then force a model or nudge a model to those observed wind fields, you can basically nail the September sea ice extent time series. So getting the right winds is a critical part of encoding the variability. And then the key point is how predictable were those winds? Of course, there's likely a large fraction of those winds that are unpredictable months in advance, but we think there is memory in the other components of the system, namely the concentration and the thickness of the ice. Yeah. So hope that answers the question to some degree.
Okay, I'm going to quickly ask you to, so there's a lot of focus on the ensemble mean in terms of the skill in the plots and perhaps the spread as well. And in the climate community, there's a lot of focus on weighting of the prediction models. Do you think there's a basis for doing that for sea ice predictions? Or is that dangerous?
Well, I found that that weighted multi-model mean I showed does pretty well if you do a skill weighting, and it's a bit tautological, but if you do a skill weighting, it does beat a naive multi-model mean. And I mean, part of the reason is that you're weighting on the skill, which is then what you're measuring. So of course the weighted multi-model mean is going to be better, but it does seem to add some notable amounts of skill relative to a naive multi-model mean. And my feeling on it is, if we've done the retrospective forecasts and we know certain systems are better and not better, I think you would want to do a weighted multi-model mean, hopefully in a way that doesn't make it, a bake-off type competition between different centers, of course. So there's a bit of sensitivity there, but certainly for the SIO, we have discussed maybe presenting a median prediction as well as a skill-weighted multi-model mean. I think would be two interesting kind of SIO sponsored forecasts to maybe provide in the future.
Ed, do you have any thoughts on that?
Yes. So I know that, and I mean, going to one of Mitch's last comments about the sort of sensitivity and not making this a kind of competition, because the CIS Outlook, I mean, the ethos of it's always been very kind of collaborative and open, right? And sort of, accepting all kinds of forecasts.
Democratic.
Very democratic, right? So each, when we create the median or each one's weighed the same. But I think in some ways that sort of brushes aside what we do know or what we do expect, that some of these systems will have better skill than others. I mean, not just say comparing with a heuristic guess, right? But I think we're probably reaching the point of maturity in the community or in this effort that I think it's probably safe to maybe start thinking about a skill weighted forecast. But again, like this is, I think perhaps something for the community of contributors to decide as much as it is for us, kind of from the SIPIN side of things.
And Wiesla, you've had your hand up. You have another question?
Just a quick follow-up on a question from Ed about the reforecast not showing the 1 year lag in terms of the skill. I was wondering if that is somehow may be affected by the bias correction that is applied uniformly for reforecast, but it's probably changing year to year on the CIS Outlook.
I think that factor could create some positive correlation in the sense that you are using last year's data to correct this next year's prediction.
Your bias correction is based on the latest years, right?
Yeah, But given that most of these systems have run for quite a few years, you're generally making fairly small tweaks to the bias correction each year. Your bias is not drastically changing year to year. So I'd be surprised if that could give you a correlation of 0.8, which is what the SIO has shown.
I'm not going to argue, but I would just say that unless we check the variability in the bias correction approaches by various groups, that's just a hypothesis at this point.
Yeah, no, I think that probably is a contributor, and it's plausible, but I can't see it being that R equals 0.8. I can't see it being that big.
Okay,
so that's my feeling.
And Megan, you can ask the last question.
Hi, this is Megan Anders with the Alaska Ocean Observing System. I'm here in Anchorage, Alaska, and I'm originally from Nome. And we partner with several Indigenous organizations on, for example, the Walrus Sea Ice Outlook. And so I'm just curious, as you guys think about your models and how you're asking your questions and what kind of questions you're asking, you might ask Indigenous knowledge holders on, what their predictions and thoughts might be that might help contribute to improving your forecasts and your assumptions and that nature. And so anyhow, I'm certainly learning and listening as I participate here. I have taken several econometrics courses, so I can understand to some extent the data discussions, but I'm just a kind of a learner observer here. Thank you.
So within NOAA, there's definitely a lot of interest in kind of expanding sort of into communicating more directly with Indigenous communities, and also tapping into sources of traditional knowledge and figuring out ways to incorporate that into our forecast assessment, and also just sort of our forecast products as well. Like we're producing things that are very kind of climate modeler centric, and quantities that nobody who actually lives in a northern community would actually probably need on a day-to-day basis. So, things like landfast ice or coastal ice conditions or ice strength, ice pressure, those sorts of things. So it's definitely an area that we're interested in expanding into, within NOAA pretty broadly. But it's been a little bit woefully short so far, I think, within our community, in my opinion. But if others have kind of tangible examples of ways that they have interacted, would love to hear them.
Okay, it's now 11 after the hour. I think Gia's hand is residual. I think we'll end here. This has been a great discussion. I'd very much like to thank both of the presenters for their time today and answering questions. And thanks to everyone for their questions. Wilbert has his hand up. Wilbert, do you have a last question?
There's the clap hand.
That's the clap hand.
That's the clap hand.
I've
Yes,
got it.
Indeed.
Well, thanks for leading, Richard, and organizing.
Okay, thank you.
Great,
And
thank
I
you.
think that'll do it. We'll have another meeting next month on another topic. Thanks very much. Bye-bye.
Thank you.
Thank you.
Everybody.
Thanks again, everybody. Yeah, that was a lot of fun.